Okay, good afternoon, everyone. It's my pleasure to welcome you all to the Collaborative Core Center for Clinical Research Speaker Series. We appreciate you taking the time to join us today for this presentation. Our presenter today is Dr. Patrick Heagerty. Dr. Heagerty is a professor and former chair of the Department of Biostatistics at the University of Washington. Additionally, he is the director of the Center for Biomedical Statistics, as well as the director of the Methodology Core for the University of Washington CCCR, the CLEAR Center. He has extensive experience as an educator, independent and collaborative scientist, and administrator. Dr. Heagerty has developed fundamental methods for longitudinal studies with a focus on prognostic model evaluation and structural longitudinal models. And he has detailed, rigorous methods for the design, analysis, and interpretation of cluster randomized trials conducted within healthcare delivery systems. His presentation today is entitled Evidence-Based Analysis of Longitudinal Data. Dr. Heagerty, whenever you're ready to begin, please proceed.
Thank you, Todd. Hey, thanks everyone for coming. I want to just give you a big picture overview of what I'd like to do in this talk. Let me make sure I can advance just fine. Not so well. Good. So I want to give this as a presentation largely focused on statistical practice. You saw in the title I said evidence-based practice. And that's really my shout out to recognizing, typically with statistical analysis, we have a lot of decisions to make. And just like we hold high standards for medical practice, that should be evidence-based, I also want us to be aware that the subjective decisions that we're making as statisticians should also be evidence-based. And so I tried to assemble some information on approaches for longitudinal data. I'll start with fundamental pre-post data. I'll bring everyone along through that. I'll take it up a notch and talk about multiple time measures and more sophisticated stuff later in the talk. So why give this talk? Longitudinal data, common, fundamental. I'm really focused on clinical trials, randomized studies. We often have multiple follow-up times. We often choose one as the primary outcome time, primary outcome measure, or maybe we summarize over a range of times for our primary analysis. Missing data is a big issue with longitudinal data. That's going to live in the background today. That's not a prominent part, but there are occasions where missing data results will motivate choice of one strategy versus another. And really why I wanted to do this was because it's my impression that there's really large variability in statistical practice. And I think we can reduce some of that variability by presenting the evidence on the options available to us. So I want to give you this slide. I don't know if there's any baseball people out there. This was something new to me. When I thought about the motivation for doing this, and I'll present the example in just a minute, I realized I was trying very hard to be good, make good decisions, but I actually made some good decisions, but I also realized later that I got lucky in some ways. And so I just wanted to bring this quote to you guys. Do you want to be good or do you want to be lucky? I think as statisticians, we're averse to being lucky. We're really hoping to be good, and I'll close with that comment as well. So I want to do part one, which was really my attempt to be good by pre-specifying the data analysis strategy for a clinical trial. I want to link that to really fundamental, simple pre-post methods. We can anchor everything really in 2 time points, and then we'll take it up a notch and talk about multiple time points. My motivation really for being good in part one was around efficiency, using really the maximal amount of information that's in a data set and not wasting any information. So I'm going to illustrate this and one other example as we go. And I'll just pause for a second and say I welcome any questions. And please interrupt me. I actually can't see the chat as we're going, so I apologize. Just open your mic and jump in. So this was a trial really looking at depression treatment strategies in dialysis patients. We published it in the Annals of Internal Medicine a few years ago. And it was a kind of canonical, small to medium-sized randomized trial looking at 2 different therapies with multiple follow-up times. We presented this as table 2, the sort of high-level summary of the results. And what this table shows is the primary outcome measure was something called QIDS-C. At baseline, we had 120 subjects. We had 2 groups, CBT and sertraline. We have the score for QIDS-C at baseline. We have it at week 6 and we have it at week 12, which was the primary outcome time. You can see our analysis says there's an approximately 1.8 point difference across the 2 groups. The confidence interval excludes the null. So we had a nominally statistically significant result based on the primary pre-specified analysis. I want to tell you what we decided to do as a primary and pre-specified analysis, and then how that would have related to other choices had we made them. This table is interesting. I'll pick out the baseline scores and the week 12 scores and talk about some interesting features in this example. And these features matter. So if you just pull out the mean scores and focus on that, we can see we had about a 4-point difference between baseline and week 12. That's sort of within each row. We had actually about a 1.3 point difference at baseline between CBT and sertraline. So there's a couple ways we could very simply analyze these 4 numbers. We could say, let's just look at the change within each group. So that would be week 12 is 8.1 minus 12.2, 4.1 point reduction in CBT. Similar subtraction of the means in the sertraline group is a 5-point reduction for an effect size or a difference across the 2 groups of 0.9. So that's one reasonable way to approach these data. Notice our estimate was minus 1.84 on the previous slide. Another reasonable way would be to say, I'm going to ignore the baseline data. That was just pre-randomization. Treatment doesn't influence that. I'll just focus on the post-only data, the means at 12-week follow-up. And there we see a minus 2.2 point difference. So right away in this example, we can see, at least without any uncertainty attached to it, the magnitude of this effect depends on how we use these data. Do we use the baseline? How do we use it? And then what about the 6-week follow-up data? In particular, there was a little bit of missing data here through 12 weeks, and we had 6-week data available. So should we use that data? And so that's really the primary focus of my talk, is what does the statistical evidence say about strategies that we should pre-specify for this fundamental problem? Here's what we wrote, and I'll translate this, and I'll say this was both good and lucky. We said, here's the models we'll use. We'll use longitudinal linear mixed effects models to compare those scores. We said we'd include fixed effects for treatment and clinical site, assuming an unstructured covariance matrix to account for serial correlation in outcome measurements. So that's something I have to unpack later. And we constrained the baseline means of the outcome to be equal in the 2 groups. And I'll make that detail clear in just a second. So we were very thoughtful about trying to leverage what randomization gave us, general differences post-line. What randomization should apply in terms of parameters is equal means at baseline, and then quite general assumptions about the correlation over time in the data. So I wanted to, ideally, I would have a reference that says, great, Patrick, you made a subjective decision. What's the evidence to support that specific recommendation? That's basically what this talk's about. So let me give you this very simple table that I think shows the thinking with basic pre-post quantitative data. And I'll focus on quantitative outcomes and linear models for this talk. What we can say in terms of parameters, what we know underlies the data, is there's a control group and a treatment group. And because it's randomized, those two groups have the exact same underlying parameter at baseline. In fact, randomization happens after baseline, so it has to be independent if it's done independent of everything. Second, we expect the control group to change over time. So now looking across the control group row, there will be the baseline value plus some time change in the control group. Or if you look on the very right column, there'll be an overall mean amount of change in the control group. In the treatment group, we expect a different amount of change. We can write that as the treatment group would have its baseline mean, the common baseline mean, plus the time effect that was in the follow-up group, plus an extra amount of change that I would blame on being in the treatment group, here listed as delta 1. So again, in the row, I could say what's the overall amount of change in the treatment group, the time change plus what we're attributing to treatment, delta t, plus delta 1. Notice this also says the thing we really care about is delta 1. What do we want to blame on treatment? We can see that in the vertical comparison at follow-up between treatment and control group. If we simply subtract the change in the treatment group and subtract away the change in the control group, we'll see delta 1, that fundamental treatment comparison. If we'd actually calculated for each subject a change and then constructed the average of that change, we'd also see the same thing. Mean change in the control group is delta t, and mean change in the treatment group is that plus whatever extra we'd like to attribute to treatment. Okay, so that's the basic data. Makes really one and only one assumption, which is randomization is independent of baseline. So it shows by randomization the two groups have the same mean. It shows we could use the means at follow-up. This is what I was really just saying to annotate that. We could take the sample mean now. The previous slide was about the parameters, the unknown parameters underlying the data. This is now about the data itself. We could say, let's just take the average at the follow-up time in the control group, and let's take the observed average in the treatment group, and we expect that statistic to capture the treatment effect defined on the previous slide, delta 1. We could do the same thing as constructing a change score, y1 minus y0, recognizing that depends on which treatment group you're in. And we can average the change in the control group, and we can average the change in the treatment group. And we could subtract the control group average change observed from the treatment group average change observed, and the expected value, that's the E thing, we expect that to be equal to the fundamental estimand, the parameter we care about in this example. Okay, I want to point out one other thing. It's a little tricky to point this out, but I want to put a third option on the table. So a third option would be to say, well, if we look at the previous two options, one way to look at them is using post only, subtracted away no baseline. Using change, took follow-up and subtracted all the baseline. There are intermediate strategies, actually, that subtract actually part of the baseline, and basically that's called ANCOVA, or a specific pre-post version of ANCOVA. So another strategy would be to take and regress, this is the idea here, put in a regression model, the treatment indicator xi, but to put in the baseline value for each individual as an explanatory variable, as something that would explain variation at the subject level. Can we remove some of that subject level variation, make our ultimate measurement more precise, or make our ultimate statistic more precise and more powerful? It turns out in this regression, beta 1 is exactly the same estimand in a randomized trial as the post comparison showed and as the change comparison showed. An easy way to say why, and there's other ways to say why, is if we took the average of this regression over the values for the baseline, conditional on treatment group, we know the expectation of the baseline doesn't depend on treatment group. So this ANCOVA model induces a relationship for the difference in the means across treatment group, where in fact it doesn't modify then the coefficient of beta 1 by the assumption of randomization, implying if beta 1 in this post-comparison model is the thing we cared about and was delta 1, then so is it sort of by reverse engineering in this ANCOVA model. Okay, so wow, there's 3 fundamental strategies that could be used for this very, very basic pre-post longitudinal data. We'll introduce another that considers really genuine longitudinal analysis, treating them both as outcomes. So the first question is, what drives choosing among these 3 strategies? And what we just showed was, in fact, each of those is a valid strategy. It gives us a statistic that has the right expected value. So then how do we choose? Well, we could choose based on which one's got the smallest variance, which one's got the most precision. I'll show you those results. Those are 30-year-old results or more. And then we'll transition and say, how does this compare to a repeated measures analysis? What if I use the baseline as an outcome and the first follow-up as an outcome and the second follow-up as an outcome? How does that strategy relate to these simple strategies? Okay, so the answer here can be given very simply and can be given mathematically. And I'll show you a graph on the next slide that says, if we make some very simple assumptions, let's just say the variance is the same in each treatment group, actually, at baseline and at follow-up, and that there's a correlation between the baseline and the follow-up measure, and we're going to call that rho, then what is the variance if you use post-only? It's the standard 2 means variance. It's sigma squared divided by n, and you have a treatment group and a control group. You look at change, it's the variance of the change in those 2 groups. You can trust me, the variance in the change has got this component, sigma squared times 2 minus 2 rho. So the comparison change to post only really depends on how big is this 2 minus 2 rho. Is it bigger than 1? It's worse than post only. If it's less than 1, it's better than post only. And ANCOVA you can derive as well. It's got a different mathematical representation, sigma squared times 1 minus rho squared, which is interesting because, again, from our algebra, that's 1 minus rho times 1 plus rho. In change, we see 1 minus rho times 1. So 1 minus rho times 1 plus rho will be less than change because 1 plus rho is less than 2, basically. All right, so this then becomes the answer in a graph. If you know the pre-post correlation, you can compare the strategies. This just says in terms of variance units, what does post only do? It always uses the variance of 2 means. It doesn't matter what the pre-post correlation is. So we can benchmark that as a 2. That'll be a comparison. Change seems like such a great idea. Let's account for baseline values. But in fact, you're taking one measurement, a follow-up measurement, and you're adding another measurement to it through subtraction. So you're potentially doubling the variance in that measurement. In fact, you'll exactly double the variance if the correlation between pre and post is 0. You've inflated the variance for the measurement you're using to compare across groups. They're equivalent post only and change exactly at that rho equals 1/2. We saw that on the previous slide. But interestingly enough, ANCOVA beats them both always. Okay, so this is the sort of first fundamental result that we know if we order from worst to best, we can have post being the worst sometimes if the pre-post correlation's moderate or strong, change being the next best, and ANCOVA being best of all. But it depends on the magnitude of that pre-post correlation. If that correlation is weak, change is very inefficient relative to post and always relative to ANCOVA. this is a result that I often quote and write into applications that use this from 1992. So we're closing in on the 30th anniversary of this basic paper. This shows in a table some comparisons, and it shows sort of the relative efficiency of ANCOVA versus POST. That's this REA versus P, and then the relative efficiency of ANCOVA versus change. It's given it as a relative variance, meaning it's always less than 1. ANCOVA is more precise, smaller variance. How much smaller variance? ANCOVA gets better and better compared to post only as that pre-post correlation goes up, and it gets relative to change, it gets less and less better as that pre-post correlation goes up. All right. I want to make a transition, but I'll pause. Any questions or comments at this juncture? Happy to take any.
And Patrick, I will monitor the chat. There's nothing in there at the moment.
Awesome. Good. Thanks, you guys. All right. So I want to say another way to approach these data. So let's get all the evidence on the table would be to put it in some sort of longitudinal analysis. Treat them both as outcome variables. Y0 is an outcome, Y1 is an outcome. That's actually what we said we would do for the ASCEND data. So we didn't choose one of those as primary. We chose a longitudinal analysis as primary. So what's the best way to handle data collected at multiple follow-up times when interest is still focused, let's say, on a fixed time? That'll spill into the average over multiple times as well. And then what about missing data? Missing data motivates a more complete, comprehensive analysis. I'm not going to say a lot about that. Okay, so again, the way we would encode this table in a longitudinal analysis is to build a mean model for these 4 cells. What is the expected value of a given outcome that depends on the time and the treatment group that measurement corresponds to? So we would build 2 predictors. We would say there's a treatment group indicator, 0, 1, and there's a time indicator. And I want to just acknowledge in this one, it's really times 1 and 2. More generally, we could encode multiple times with multiple dummy variables. So if I encode this structure in a mean model, it says there's a time effect and there's a treatment by time effect, but there's no treatment main effect. This model uses randomization, that fact, to constrain the means to be equal at baseline. Okay. Does that look like one of the other pre-post methods? I'll show you exactly what that looks like. And then I'll show you what a more maybe natural first thought longitudinal analysis that you might specify, which would put in the treatment main effect. What does that give you? What's the cost of putting in that, what one could say is extraneous parameter? Okay, so there's a result, and I'll spare you the details, but I'll give my statistician friends a hint at where this comes from. The result is the ANCOVA estimator of the treatment effect is mathematically exactly equivalent to the maximum likelihood estimator of beta 2 in this longitudinal linear mixed model. So if you liked ANCOVA, you should like this model. There's a couple nuances about that relationship that's important. You use this mean model, don't put in that extra treatment effect at baseline, and you use a separate variance at each time point. In this example, there's only 1 pair of times, so there's just 1 correlation. And we can show this, and we've shown this just by factoring the joint likelihood. What's the likelihood for Y0 and Y1 given covariates? We can decompose it into Y1 given Y0 and then Y0, and Y0 is the part that has really no information about treatment in it because that's pre-randomization. So link number 1, a longitudinal analysis with this specification is with complete data mathematically equivalent to ANCOVA. And that's why we chose this analysis as primary. All right, I want to I want to transition now and show you an example with multiple time points, and then I'll come back to the motivating example and round that out as well. Here's another example. This is another very small, lovely data set. It's 50 placebo and 50 active. It's from Garrett Fitzmaurice, Nan Laird, and Jim Ware's book. It was a placebo-controlled randomized trial of a chelating agent, sort of pull lead out of the blood, called Sussimer. It was conducted among kids that had pretty high lead levels. Notice the entry criteria is 20. They received up to 3 26-day courses and were followed for a long, long time. It's stylized because it's balanced. Everyone's measured at the same times, and it's complete. No missing data in this example. Here's what the means look like over time. Again, entry eligibility on the y-axis is blood lead, on the x-axis is time since baseline. We can see, wow, a huge effect immediately. We can see that the treatment effect starts to wane. Had we said 6 weeks is our ultimate time of interest, we can still ask the question, is there evidence that that's statistically significantly lower than the control group? So sort of a great example where a time course may differ in each group. We have to identify the estimand. What is it exactly we want to test or make inference about based on the groups over time? And then we need a strategy to do it. I want to point out something we haven't really looked at yet. We've really focused so far on the mean. What do we see in the groups and their means over time? Here for this data set, I want to show you the correlations over time now. This is a part of, I think, regression that we often give second seat to. We sort of focus a lot on the mean model and then kind of quickly talk about the variance model or the correlation model. And I really want to emphasize the importance of thinking about this model too. This is an interesting example, right? This shows a correlation matrix on the left for the placebo group. I put a purple box around the correlation between baseline and the 1 week, 4 week, or 6 week measure. Very strong pre-post correlation between baseline and each of the follow-ups. Notice the baseline becomes a slightly weaker predictor at the week 6, maybe. 0.76 is the correlation versus 0.83 and 0.84 earlier. However, in the treatment group, the pre-post correlation is weaker. It's 0.4, 0.38, and 0.5. Okay, is that plausible, or is that just noise? I would say it's quite plausible when there's heterogeneity of response to treatment. Then there's more variability in the treatment group, and there's potentially less correlation in the treatment group. We see hints of that here as well. If I look at the variances in these two groups, what's the variance? Perfectly equal at baseline. That's sort of lucky statistically, but a 25 unit variance at baseline. In the placebo group, the variance grows to 30, 33, and 32. In the active group, the variance jumps to 60, 62, and 85 at week 6. So notice we focused our inference on differences in means. We've talked about different fundamental strategies for evaluating those means. What are the strategies and what are the guidances for thinking about the correlations and the variances? All right, this is a demonstration. If I'd done it time by time as pre-post only data, everything lines up beautifully with Frisson and Pocock. If I looked at the week 1 effect, post-only change or ANCOVA, all around 11 points. The standard error, post-only 1.3, which is bigger in this example than change, which is not much bigger than ANCOVA. We saw on the prior slide, if you assumed a common correlation, it's somewhere between 0.5 and 0.8. So it's in that relatively high pre-post correlation where change can still be competitive. Similar patterns at week 4 and similar patterns at week 6. Okay. What our prior slide said was, transition, and then I'll come back to longitudinal analysis. Transition is to say, I'm talking about randomized pre-post data, and I want that to be clear. If it's not randomized, I can't say the baseline difference is 0. I would definitely and naturally put treatment effect in the model. And now all my estimands differ. The follow-up difference is delta 1. The difference in change is delta 1 minus delta 0. I just want to recognize the design matters for this particular approach. And I would approach it differently with a different design. But my goal here was to really talk about randomized designs. Okay. Had I put this in a longitudinal model, like I described earlier, actually a more general version with multiple follow-up times, multiple treatment by time interactions, no treatment baseline made effect, and one common variance covariance matrix, then I get the following results. If I make the assumption of equal means at baseline, this longitudinal analysis recovers very closely. The point estimates are identical. The standard errors are ever so slightly different. So I wanted to just say to you all, this is an empirical demonstration, actually, that the longitudinal analysis with the baseline constraint recovers the ANCOVA time by time. This is a complete data set, so it should recover it time by time. I also wanted to say, if I put that unequal baseline in the model, if I put the treatment main effect in the model, I actually recover the change analysis. So this is the second link I want to give back to you. If you would have used ANCOVA and you would have been concerned about change being inefficient, then the longitudinal analysis should not put that treatment main effect in the analysis. That then makes that longitudinal analysis, this longitudinal analysis, equal to the change analysis, the less efficient analysis. Okay. So now we've really put 5 options on the table. I want to then come back to this issue and talk about the phenomena I started to show you that I was worried about. But I want to say this was the end of me being good. And what comes next is me being lucky. What this shows is a couple relationships. We can say constrained pre-post longitudinal data analysis is equivalent to ANCOVA. It's lovely in the fact that it uses all the data that's available, even when there's missing data. There's an appeal to missing data and robustness, something called missing at random in the linear mixed model may have some benefits. That's a very limited promise, I would say. It depends on the correctness of the linear mixed model. It must be 100% correct. And it depends on whether there's other extraneous factors that may predict missingness that are not in the linear mixed model. It's really when you're thinking unfolding outcomes drive missingness that this is a good strategy. How do we generalize it to multiple follow-up? And then I think we saw when we looked at the variance covariance, there might be some issues about the changing association between baseline and follow-up. And in fact, we saw some potential changing associations between baseline and follow-up, depending on which treatment group you were in. The pre-post correlation looked to differ in those two groups.
Patrick, can I ask a question?
Sure.
Hey, this is Paul Nider. Thanks
Paul.
for your talk. Hey, so when you're in that longitudinal analysis, are you treating the baseline value as a covariate then, or are you treating it as an outcome, like a dependent variable?
An outcome.
Okay.
An outcome. An outcome. Okay. And I'll make that clear again, Paul, on right. in a few slides. And then I'll leave time at the end. I'm definitely going to punt one small section at the end. But all of the longitudinal analyses, I'm really referring to the analysis where they're all outcomes. All right. I want to say how to do this as well. Like, how do you do this in software? I also want to say, like, this is recognized by the FDA. There's guidance document came out in April 2019. It says, hey, sponsors can use ANCOVA. Pretty cool. It's like surprising that it was a hard statement for FDA to make, but it's basically saying it's okay to look at treatment effects adjusted for for covariates, okay? It's interesting, if you look in the details, hang on, I guess I'm using different advancement. I'm gonna be careful. I want to point out a couple things in that document. It says the interaction of a treatment with covariates is important, but the presence of an interaction does not invalidate ANCOVA. We're going to talk more about that. What if the baseline was used as a predictor, but what I showed you was true, the pre-post correlation differed by treatment group? Well, then the effect of the baseline depends on treatment group. ANCOVA, still valid. The second point, it says at the bottom, many trials use change from baseline as a primary outcome measure. And even when you use change from baseline, the baseline value can be used as a covariate to explain variation. In fact, it's redundant. It turns out if you do change given baseline, that's exactly the same as follow-up given baseline. So ANCOVA is legal. And the longitudinal analysis with this constraint reproduces ANCOVA. This was me being lucky. I gave a very simple covariance matrix because it didn't depend on treatment group, and I want to talk about that. So look at this. Like, I want to go to really fundamental stuff. If I said you've got a 2-sample trial and you're going to do post-only analysis, that's a 2-sample test of means. You're going to give me a confidence interval for that mean difference. A really easy way to do that is to stick it in a regression. This is LM is R speak for linear model. Just regress that outcome on the treatment indicator, read off the coefficient, and read off the standard error. What if, in fact, the variance is different in the treatment group as compared to the control group? Fundamental scenario. This graph shows what do you get as the observed variance for the statistic that you're reading off, and what do you get from that linear model output, the estimated standard error that's assuming, in fact, the variance is constant across both groups. And notice you get huge differences depending on which group is enriching the overall variance. If the group with the big variance is enriching the overall variance, then the estimated standard error is going to be too big. If the group that's contributing more as the smaller variance, then the estimated standard error is going to be too small. So this, I would argue, we often don't think about this. Maybe you guys are amazing in your practice and you would never read out the linear model coefficient, or you always use robust standard errors. But in fact, or you're like me and you're lucky that you always use 50-50 randomization. This graph shows this other result that says, in fact, the unequal variance won't hurt you when you assume it's constant, if in fact it's 50-50 randomization. So you're all breathing a sigh of relief, like, oh wow, I don't think about this very often, but I'm often in this 50-50 spot, life is good. I want to make you nervous again and say, but if you had 3 groups, there's no guarantee now. If you had encoded those 3 groups with 2 dummy variables, x1 for treatment group 1 relative to placebo, let's say, x2 encoding treatment group 2 relative to placebo, and treatment group 0 and treatment group 1 had the same variance, but treatment group 2 had a multiplicatively bigger variance. What do you get as the ratio on the y-axis, the standard error you're reporting versus the variance in truth? And the answer is, as soon as you move away from that constant variance, you're going to get one of the groups standard error overestimated, and you're going to get one of the groups standard error underestimated. So even in the simplest examples, think about the relationship between treatment group and variance covariance. Ensure your procedure is attentive to that by introducing it to the model, by introducing robust standard errors, or by knowing you're lucky that 50-50 actually in a 2-group setting will work. So I wanted to say, for longitudinal data analysis, this kind of phenomena, the variance across treatment groups, I think is generally overlooked. I overlooked it, I would argue, in that pre-specified analysis plan I just showed you. So what is the impact on validity? What is the impact on efficiency? I also want to say I think these issues are also similarly underappreciated in other places that were sort of heavily model-based in our primary analysis, like cluster randomized trials. I'm gonna tackle a couple highlights, and then skip a section and then take final questions. I want to say there's this amazing paper that's 20 years old that I didn't know about for a really, really long time. It's by Yang and Ciatis, 2001. They really give great detail on these issues that I've started to talk about, sort of moving pre-post and ANCOVA into a longitudinal analysis framework. They talk about GEE, a generalized estimating equation strategy. They actually introduced something, to me at least, called ANCOVA 2, which is distinct from the ANCOVA I just showed you. And then talk about equivalence between strategies under the assumptions exactly that I showed you. There's a restricted moment assumption. The means are equal at baseline, and you can further constrain the variances at baseline. Go read this paper. It gets a big gold star from me, as you can see in this slide. It emphasizes equality of means, equality of variances, and it emphasizes separate post-baseline covariances. This has kind of picked itself up in this literature that informs the FDA guidance document. There's this paper by Wang, Ogburn, and Rosenblum that talks about ANCOVA and robustness, and then Bartlett that corrects and says that's for the 50-50 case. Actually, be careful about generalizing that earlier paper. All right. I want to show you this example. So again, our analysis, ultimately, this minus 1.84 was from a longitudinal analysis that I introduced to you. All three, baseline, 6, and 12, are outcomes, dummy variables for time, equality across groups at baseline, and one common unstructured covariance matrix gives this estimator minus 1.84. But if we then look in these data, now let's do the questioning. Does the covariance matrix look the same across the two treatment groups? So on the left is the empirical covariance matrix stratified by each group. On the right is the empirical correlation matrix over time stratified by each group. A couple things to point out. You know, the variances, if I look at time 6 and time 12, they look bigger in the CBT group than in the sertraline group. Baseline, they're pretty similar, 24 and 26. If I look at correlations then, in the CBT group, baseline has a correlation of 0.32 with the week 12 outcome. In sertraline, baseline has a correlation of 0.09, empirical, with the week 12 outcome. So does that say, in fact, I should use and subtract off in ANCOVA more baseline from the CBT group because it's useful, and less from the sertraline group because it's really going to introduce noise? If I had that line of thinking, what it would make me do is to take ANCOVA and say, I want treatment plus baseline, but maybe the baseline predicts differently depending on the treatment group. Well, now I'm starting to get unhappy. I didn't really want to talk about a heterogeneous treatment effect that depends on baseline, but I did want to acknowledge maybe the baseline is differentially useful for precision. This is called ANCOVA 2, actually, by that prior study. So there's definitely implications for considering the covariance and then considering how might that manifest in the strategy that you're working with. Relatively easy in a longitudinal strategy as compared to ANCOVA, just to give separate variance covariance. Don't change the mean model you want to characterize, but definitely think about the variance covariance. So I wanted to really get to this slide, and I did it today, which is good. And I'm going to skip a few things. And I appreciate you hanging with me. I'm sure I had most of you for a while, and I hope I've got some of you still. But I would like to sort of land here and say we have an evidence base that guides a complex statistical practice decision. Fundamental randomized trial. Should we do a change analysis? In this example, for motivating depression study, should we analyze change given treatment? Should we do ANCOVA 1? Adjust for baseline. Should we do the longitudinal version of change, treatment plus time plus treatment by time with one unstructured covariance matrix? Should we do the longitudinal data analysis that's constrained? That's what I called constrained 1. It's the outcome depends on time and treatment by time, but no baseline. I emphasize that ANCOVA 1 and longitudinal analysis, these are equivalent. I demonstrated that the change analysis in the longitudinal framework and in the simple framework are also equivalent. What this other work then pushes us to ask is, should we really move beyond this common variance covariance matrix and leverage what we know, which in this particular Yang and Siatis paper, they say still use a common variance at baseline, but use separate variance covariance matrices depending on which treatment group you're in overall. Or should you just take fully separate variance covariance matrices? Okay. So let me take 5 more minutes and show you 2 things. In our example, here's the results we would get. So I could take 1, 2, 3, 4, 5, 6 of those strategies. Maybe that's all 6 that I just showed you. I did show you 6. And apply them to this example. Notice the change analysis gives minus 0.9. It has the highest standard error, 1.14. Had we analyzed change, we would have been very inefficient. We actually would have lost the statistical significance in this example. So it's really a fundamental illustration. We pre-specified this. You have to trust us. You can see the documentation. We said we would do this one. The one that's called LDA ANCOVA 1. That's our pre-specified analysis in these data. Had we done ANCOVA, we wouldn't have used all the participants because some would have been excluded due to missing this. We would have gotten a very similar estimate. In fact, we're 99% of the variance of that. We didn't gain much efficiency by doing what we did. Had we done the unconstrained longitudinal analysis, again, we would have lost enormous efficiency. Standard error 1.14 as opposed to 0.88, which ANCOVA or this constrained longitudinal analysis would have given us. Had we done more sophisticated things in our example, it didn't much matter. This was 50-50 randomization. What I can leave you with is that makes us lucky, and we can show similar results. I won't have enough time today to say what happens when you have separate covariances and you don't acknowledge it. You can get lucky and still be valid, or you can be impacted and have the validity of your inference damaged. A couple things. I want to say R has this amazing function. I've used it here and I've illustrated it in the syntax, this GLS function in this NLME package. And we've learned how to talk to this package to get the models that I just showed you. And I'll just show you one, you guys. Here's one. Here's the basic one, which is to say our pre-specified analysis really would give a common correlation across the 4 follow-up times, give 4 separate variance parameters, or here it's a ratio, how much bigger does the variance grow from week 0, week 1, week 4, and week 6. But there's this amazing, clever syntax. And then that shows up in the standard errors, right? That's really important because that's what gives the standard errors for these effect estimates. So the week 6 treatment effect -3 points with Sussimer, 1.25 standard error, significant nominally 0.013. But this package has incredibly clever syntax. You can code a variable to talk about the variance you want. So here's an example where I actually Tessa Rue, my collaborator, who's amazing, said, I want the treatment groups to have the same variance at baseline. So I'll code those as 1s, but I want the placebo group at time 1, 4, and 6 to have different variances. So I'll code those as 2, 3, and 4. And I further want the intervention group to have even different variances. I'll code those as 5, 6, and 7. Or you can code time. I'll pretend the placebo group is times 1, 2, 3, 4, and I'll pretend the intervention group is times 5, 6, 7, and 8, and I'll use clever tricks to encode the covariance groups separately for those two groups. So I think there's not a software excuse anymore not to do this. This is what comes back from that clever coding. It shows the correlation matrix in red for the placebo group. Recall, we saw it was really high, like 0.8. That's coming back. How about the intervention group? Descriptively, we saw that was much lower. That's coming back as well. And rats. As well as the variances, we can get different variances. So I wanted just to say, in closing, this is an issue. I think it's been underappreciated. We should think very hard about it. I think this work is we've taken it a little further, and we've tried to characterize the impact of those issues. I guess I'd like to just close and say, I really want to go back to this slide. Sorry, I keep messing up choosing the button. I want to just say, I skipped a little bit, apologies. Change over time is central to all comparative effectiveness research. Randomized designs, we have to do optimal procedures to gain power for the investment. And COVA has optimality properties for a single time point that transfers to a specific longitudinal data analysis with that constraint at baseline. And then the second half really talked about my pre-specified analysis wasn't sufficient. I'd go back and do it differently, but I was lucky because it was that 50-50 spot. I think we should use separate covariances across treatment groups to ensure validity. There are alternatives. Use a robust variance, for example. This also asks questions like, well, how do you generalize this to binary data? And I think much of the parallel in thinking, what can you assume based on randomization and what can you keep as flexible as necessary, translates to that setting as well. We haven't studied it very hard. And then this is sort of where I am today. Like I said, do you want to be good or do you want to be lucky? I said I was trying to be good on the mean and I got lucky on the covariance. And so I'm still working on being good and good on both elements so I don't have to rely on getting lucky. Thanks for your time, gang. I appreciate it.
Well, thank you very much, Dr. Heagerty. We have time for some questions. And as a reminder, you can either type your questions into the chat or if you want to unmute yourself and ask a question, you are welcome to do so.
Quick question following up. Can you talk for a second about % change as an outcome? I mean, I know that's not a good way to analyze it, but there's something fundamental that I like about the % change as a way to describe what's going on over in longitudinal analysis.
Yeah, it's interesting. So, Paul, we often use it for a success. It's the ingredient to a success indicator sometimes. Was there 30% change or not? right? So I'm taking it one step further and saying that's a prelude to often converting an analysis based on means into an analysis based on success. 30 or 50% improvement in function, 30 or 50% improvements in pain. I haven't thought about it in the context of this talk, Paul. I've separated that in my mind. That would be a different way to think about using the baseline. There are some additional things I know people have thought a lot about, which is the impact of measurement error in that strategy. And so I think I don't have a lot to give you as an answer, Paul. Could be okay. Others have thought a lot about that. I can point you to some of the literature I know on that. It's relatively old.
Okay. Thanks.
You're welcome.
So there's a question in the chat sort of asking about a Bayesian approach as an alternative strategy. I don't know if you have any thoughts on that in a general sense, if that would be something comparable or preferable.
This work fundamentally talks about the likelihood, right? And so I think this work applies to Bayesian analysis. I would say this work focuses on the likelihood. And so I would say, please look at it and take it into a Bayesian analysis. Think about the issue of common covariance, actually. Think about the assumptions that randomization gives you and be aware of how that should show up in the specification of the outcome given randomization in time. I would say that would be the most important message I'd want to give. I don't have a strong preference for whether you put this likelihood into a frequentist evaluation or a Bayesian analysis. I think this is really talking about maximizing robustness by being attentive to the nuances, the known nuances that are in the likelihood itself. So be aware of your assumptions, actually, whether you're frequentist or Bayesian.
So based on your response, this could be a related question. I'm curious, you have laid this out in the framework of a general linear mixed model. If you were to be fitting a GEE, generalized estimating equation model instead, what do you have any general kinds of comments along those lines?
Yeah, I haven't explored how to do it and I haven't studied it, but I would go back to this that says the fundamental mean structure says don't waste precision by putting in a treatment main effect. That's what happens with change analysis. You basically throw away some information. So use this mean model with binary data. This says use an unstructured correlation matrix for the outcomes. Don't make it exchangeable. I mean, it says basically if you do that and robust standard errors, then you're protected against this concern in terms of validity. Did you leave some efficiency on the table? That's going to depend on the randomization fraction, I think. So what I like about this structure is I think it gives guidance, although it's not been completely studied. I haven't done the work for the binary data that can defend that. So I want the evidence. If we want to be evidence-based, I would say this provides a body of evidence around the basic structure. And I think it gives insights in how to take it to count data or binary data. Great question.
Great. Well, I think we're at time. Thank you again, Dr. Heagerty, for taking the time to talk with all of us today.
My pleasure.
Prior to everyone leaving the meeting, we do ask that you complete a very brief survey that has been launched about today's excellent presentation. Thank you for attending the talk. Have a wonderful day. Thank you again.